Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Episode 3.4.2, Supplemental, Unscripted Thoughts on LIGO. So hello, this is something a little bit different. Every so often in science, something happens that causes me to have to break into the regular history or philosophy of science feed to talk about the event. Now, normally I don't do this. This is not a current event science show. There are some of those out there that are really fantastic, things like Star Talk, Titanium Podcasts, and the Infinite Monkey Cage. But sometimes something happens that's just so important that I need to sort of break the narrative, get in and talk about this. And so that's what we're going to do this week. Last time I did this was when the Rosetta orbiter dropped the Philae lander on Comet P67, and I had to talk a little bit about that. Well, this week we've got a similar sort of really big announcement out of the community of cosmology and physics that I'd like to talk about. Now, one thing just really quick here before we get into the show, do understand that this is completely unscripted. This is just me sitting down, and I've got just a very rough outline, and I'm just going to share some thoughts about what's been done with the LIGO Observatory and what that all means and some of the science that goes on around that. So this will not be as polished, but hopefully this rawer kind of format maybe will also be engaging to you. At least that's my hope. So welcome to the podcast this week. We'll get back into the typical sort of history and philosophy of science narrative of finding our place in the next episode. I've got a great script pretty much finished on Babylonian astronomy that I'm going to share with everybody. The nice thing about this, it gives me another week or so to do some more research on that to really bring that show into some great focus, and also to get ahead again. I'm starting to run out of some of the material, so this will give me a chance to get back ahead on that part of the project. So let's talk a little bit about what we're going to do today. I want to talk a little bit about this discovery that got announced on Thursday from the LIGO project, which means there are a few things I'm going to take you through. First, we need to sort of talk a little bit about the idea of what LIGO is. We need to talk a little bit about general relativity and why that's important. We'll talk about what LIGO did, how it works, how it got conceived, how it was funded, how the data processing happened, all of those sorts of things. And then we're going to talk a little bit about just a bit of the history there. And then we're going to discuss what that discovery means, why it might be important. And then there was an interesting thing. There was a little bit of a controversy that came up with all of this that I want to chat about. And then we'll sort of look at putting this in sort of a context of how important this discovery is and then wrap everything up. So that's sort of our outline for today's conversation. So the first thing we need to talk a little bit about is what is LIGO. At least that's what I call it. I've heard people call that acronym a whole bunch of different things. I'm going to call it LIGO. And it stands for Laser Interferometry Gravitational Wave Observatory. And so the first thing we really want to talk about is what is this thing? What is LIGO? And the best way to sort of talk a little bit about this is that it's a telescope. Quite frankly, it's really what it is. When we talk about a telescope, normally we talk about a piece of equipment that gathers light waves, concentrates them, and then takes that concentrated light and puts it into an instrument for analysis. When telescopes were first developed, of course, that instrument was our eyeball, but no astronomer actually looks through a telescope to do research with their eye anymore. There's always some sort of an instrument that can quantitatively gather data, whether that's a spectrometer or a CCD chip or something of that sort. Well, this is a type of telescope, except that it doesn't use light waves to make observations. It uses something very different. It uses something we call gravitational waves. And we're going to talk about what those are and why they're very different and how that works. There are two of these telescopes. One is in Livingston, Louisiana, which is near Baton Rouge. And the other is at the old Hanford site out in eastern Washington state where some of the really amazing work for plutonium production was done in World War II and following. And so these two telescopes were really brought online back in 2002. They were conceived in 1992, but they were brought online in 2002 originally. And over the last 15 or so years, they've been doing work, and they just announced this discovery of a gravitational wave signal. So the discovery announcement said that they had observed the gravitational wave signal from two massive black holes that had been orbiting each other. That orbit had decayed. In other words, these two guys had spiraled in and had merged, and that process had been observed by the two telescopes. The merger, the two black holes were about 1.3 billion light years away from the Earth, which says something about how long the signal had traveled through space to get to us. And that these guys had observed not just the merger, but the run-up to the merger to some degree. And so that's a really big deal. And this is the first direct observation of a gravitational wave signal. We're going to talk about this idea of indirect and direct observation a little later on in today's podcast. This project was broadly funded, not completely, but broadly funded by the National Science Foundation here in the United States. And it represents the single biggest funding initiative that the National Science Foundation has ever undertaken. And the National Science Foundation took some criticism over the years for doing this, but I think it's safe to say that all of that funding is now paid off, and we'll talk about why that's very important. So that kind of gives you just a very, very brief overview of the announcement and what's going on with that. But obviously there's a whole lot more that we want to dig into to get a better sense of what the announcement is really about, what it means, and why it's so important. So to start off, what we really need to do is we probably need to build a little bit of theory here to just get a sense of what a gravitational wave is and why it's an interesting thing for us. So to do that, we've got to go back to 1905 and Albert Einstein's work in what we call now the special theory of relativity. And I'm not going to go into the whole details of this. We'll do that later on in this series of the podcast that we're in the middle of. But Einstein's first papers on this in 1905, we now call the special theory. And in that, he comes up with a very different description of the nature of the universe. Prior to 1905, we were working on what was sometimes called Galilean or Newtonian relativity. And in that, what we thought is that there were three spatial dimensions. You might think length, breadth, and depth. But that time was sort of an absolute invariant. It was very completely different than those three spatial dimensions. And Einstein was working to solve a problem in that James Clerk Maxwell's equations that described electromagnetic waves didn't behave the way they were supposed to mathematically in that kind of a system. And he was trying to figure out how he could get that problem solved. It was one of the big questions about Maxwellian electrodynamics, is that it didn't work correctly. It obviously produced predictions of behavior that were accurate, but it didn't do some of the things it was supposed to do. And it turned out that in sort of examining that, he came up with a very different description that turned out to resolve all of these kinds of problems that you had with Maxwell's equations. And that description was that there were not three dimensions of space and then in a separate sort of absolute time. He said, look, time is not something different than space. That time, especially if you take time and multiply it by the speed of light, it becomes its length. And because of that, it gets added in as a fourth dimension, something he calls space-time. Now, this is a really, really difficult thing for the human mind to wrap itself around. And that's because it's impossible for us to conceptualize things we don't directly experience, and we only perceive in three dimensions. And so we can perceive depth, we can perceive width, we can perceive height, but what we cannot perceive is something that's at right angles to those three things. And so it's one of those things that your brain just doesn't get itself around. The best thing we can do is we can sort of look at three-dimensional shadows of four-dimensional objects, things like hypercubes and that sort of thing. And I'm not going to go too far afield on that in this episode. We'll come back to it later perhaps. But he comes up with this description called space-time, and he recognizes in coming up with this description, he says that, okay, all of the things in this description are all moving at constant velocity, which is why it's the special theory of relativity. He then takes another 10, 11 years to sort of work out what happens when he considers the more general case of reference frames that can accelerate. And so it's 100 years ago this year, in 1916, Einstein publishes his general theory of relativity. And in that general theory of relativity, he's not only talks about space-time, which has already been established in the earlier papers, but he talks about how gravity works in a very, very different way than Isaac Newton had in his universal theory of gravitation. And in that universal theory of gravitation, the sort of the description is if I've got two fairly massive bodies, let's say I've got the Earth and I've got some big asteroid or something coming by the Earth, what we know is the Earth will deflect the path of that asteroid. And Newton's laws say that an object in a state of motion moving in a straight line should remain in a state of motion moving in a straight line unless acted upon by an external force. And so if that asteroid's path is deflected from a straight line in some way as it goes near the Earth, what that means is, according to Newton, there has to be a force. And so Newton comes up with a force that he calls gravitation, and he comes up with a force law, what we call the universal law of gravitation, that describes that really well. And that universal law of gravitation had worked for hundreds of years. But in the 19th century, it began to be realized that there were a couple of things that it didn't quite handle really well. The most important, probably the most common one talked about, is the orbit of Mercury around the sun wasn't quite what Newton's universal law of gravitation predicted it should be. And so when Einstein does the general theory of relativity, his description becomes a very, very different thing. And what he says is, you have this fabric of space-time, and instead of us thinking about gravity as a force, what he says is you're going to think of gravity as a warping of that space-time. And I'm going to come back and give you an analogy that will really help you here in just a minute. So hang with me as I go through this. But he says mass warps this space-time. And then this asteroid doesn't feel a force. It just travels on its natural path through that warped space-time, which is no longer going to be a straight line. And so the common way you hear this talked about is that mass warps space-time. Space-time and its curvature tells mass how to move. And so let's talk about this analogy. I think that'll help you sort of visualize this. Again, part of the problem with trying to understand this is if we talk about something like flat space-time, is I'm going to talk about that, and I mean we're talking a flat space-time in 4 dimensions, which is just, trying to talk about what flat means in a 4-dimensional something is just impossible, right? I mean, it's hard to talk about what flat means in a 3-dimensional sphere, for example, or something. To try to talk about it in 4 dimensions is really hard. So, as we often do in science, let's simplify this system down significantly. And the most common way you think about doing this is you sort of think about, let's, instead of thinking of 4-dimensional space-time, let's think of space-time as a 2-dimensional sheet. And oftentimes what you'll see folks will represent the sheet as some sort of like flexible latex sheet or something like that. I think probably the best way for you to maybe think about this is think about a household trampoline, you might have your kids or your family over to bounce up and down on. And the trampoline, of course, what you know is that there's this membrane, made of something stretchable, be this sort of hung from this hoop by a bunch of springs, and there's some tension in that, right? And so that it's flat, okay? But it's not rigid, okay? So now, if I were to take in that flat sort of surface and I were to roll a ping pong ball across it, of course, the ping pong ball, if we could ignore friction, would just move across that flat surface in a straight line. Now, one of the things we've got to be a little bit careful, and I'm not going to go into too much detail on this, but a little bit careful is this. Normally, when you see this flat surface, what everyone thinks is they tend to think in terms of length and depth, in the X direction and in a Y direction, and they think the ping pong ball rolling across that. And that's not actually exactly correct. What you actually have to think about is that one of those dimensions has to be that sort of time dimension, but that's probably a little more than we need to dig into right now. So what Einstein's model says is, if we look at what mass does here, it would be like taking that trampoline surface and putting a really heavy thing right in the middle, maybe like a really heavy bowling ball. You get a 16-pound or an 18-pound bowling ball or something, and you stick it right in the middle of that. In your mind's eye, I think you can sort of think of that membrane, that surface of your trampoline, warping or curving to create a depression right where that bowling ball sits in the middle. It pulls it down and creates a warped surface, or what I think of as warped space-time in 2 dimensions, in that particular surface. Now, if I roll my ping pong ball across that surface now, if it gets fairly close to that heavy bowling ball, what it's going to do is it's not going to be traveling across a flat surface anymore. That surface will be warped, and so it will no longer travel in a straight line. And that's not because the bowling ball is exerting any sort of a force on the ping pong ball. It's just that ping pong ball is following the curve of the trampoline surface, which will cause it to change its direction of motion. It will no longer move in a straight line, but it'll move in some sort of curved path. And that's a nice analogy of thinking about Einstein's description of curved spacetime. Okay, so that's, general relativity in just the briefest nutshell, right? So Einstein predicts a whole bunch of things are going to happen because of this description. And so over the last 100 years, in time, we have confirmed every one of those predictions. And general relativity is probably one of the most, if not the most tested scientific theory humankind has ever come up with. And it has passed every single test, even as it's very counterintuitive. Okay. It correctly predicts the motion of Mercury around the sun. It correctly predicts the deflection of starlight by the sun from stars behind the sun as they would come towards the Earth. That was an experiment done by Arthur Eddington in, I think, 1921. One of the predictions that Einstein came up with were these things he called gravitational waves. And what he said is, look, if you had something really heavy, really massive, that really caused the fabric of this space-time to warp a lot, and if it did something in that space-time, it would produce waves in that space-time, a little like dropping a rock in a pond, and it creates ripples that sort of propagate outward from that point where it got dropped. A similar kind of thing might happen in the fabric of space-time, that if some very massive object, or actually if any massive object were to do something, it would produce these waves. But the largest waves would be produced by the largest objects. And so one of the things he sort of suggested, though, was when he did his calculations, it turned out that the size of those waves, even for the largest objects that he could imagine, would not be easily visible. And so Einstein said, look, we're never going to be able to observe these. He said we'll never be able to sit down and actually see the amplitudes necessary. We just don't have the equipment. And so it was one of those things where it's kind of, for a long time it was sort of the last of Einstein's great predictions that there would be gravitational waves. And the thing that everybody sort of said, well, at least Einstein anyway said this just isn't going to happen. The thing Einstein didn't see coming is he didn't see big science. Okay, when Einstein does the general theory of relativity in 1916, there's no big science. Okay, almost all science is still being done on a desktop. At least all physics is being done on a desktop in experiments like Rutherford was doing at Cambridge by then, and certainly at Manchester or McGill earlier. And so, what he doesn't see coming, is he doesn't see in 1932 that Rutherford's going to build the first big particle accelerator at a lab at Cambridge there at the Cavendish Laboratory. He doesn't recognize that guys like Lawrence are going to build cyclotrons that are going to be big science. And he certainly doesn't foresee what's going to happen in World War II, where you're going to see huge machines being created to do physics, okay, things that create and separate things like uranium or plutonium to produce weapons. And so coming out of the war, we now have this apparatus where we're creating very large machines. And of course, probably the biggest of those that you can think of are these huge, massive particle accelerators that begin to come out of that period after World War II. And those culminate, of course, in the ring at CERN, which is 27 kilometers in diameter. It's this huge science machine. And it's the epitome of what we call big science. And Einstein just never saw that coming. It's not something he foresaw happening. But it has happened. And so because of that, people began to sort of say, are there other ways to think about maybe being able to make those kinds of observations? And it turns out somebody had this great idea. And what we had to do is we had to do some more work in Einstein's general theory of relativity. But when pulsars were first theorized and then discovered by Jocelyn Bell, it was recognized that there would be these very compact, very massive objects running around in the universe. And so it was recognized that these objects might be massive enough to actually create a detectable gravitational wave. But maybe we didn't have the equipment to do those. But a couple of individuals, Russell Allen Hulse and Joseph Houghton Taylor, out of the University of Massachusetts in Amherst, had this idea that maybe if you had a couple of these neutron stars, these pulsars, in orbit around each other, by looking at their orbital dynamics, which is something you could do with a radio telescope, you might be able to recognize that as they lost energy due to sending these waves out, that you might be able to do a calculation on that. And so in 1974, they found a candidate pair. They found a pair of pulsars orbiting each other. They used the Arecibo radio telescope to make observations of those pulsars, realizing that the timing of the pulses that came from these two super compact objects was changing. They were able to model that change by saying, hey, if these gravitational waves that Einstein predicted did exist, they would take energy out of that system in a very specific way, and that matches our observations very, very closely. And so that was sort of an indirect observation. You weren't actually observing the gravitational waves themselves. What you were doing is you were observing the consequences of the behavior of this system, these two co-orbiting neutron stars. And in doing that, you sort of got results that were consistent with the presence or existence of gravitational waves. Hulse and Taylor will get the 1993 Nobel Prize for this work. It's phenomenal work. But note, it's an indirect observation of gravitational waves. Nobody in that approach had actually directly observed these things. Now, for most scientists, that piece of work, which is why they won the Nobel Prize, that piece of work was considered sufficient evidence for the existence of gravitational waves. But, big science marches on. And so what happens is this big science approach begins to, in the 1980s, people begin to think about a way to maybe make the kinds of observations that would directly observe gravitational waves. And this is where LIGO comes in. So a little history on LIGO, just very quickly, and then we'll talk about how it works. The guys who sort of come up with the idea are Kip Thorne, who is just a really well-known cosmologist and relativistic physicist. Donald Driver and Rainer Weiss conceive of maybe putting this kind of a project together in 1984. And they kind of put together some plans. They do some sort of, hey, this is how this might work. This is how we would put things together. And they write and present a proposal to the National Science Foundation, which in 1992 gets funded. Okay. The National Science Foundation said, we think this is fantastic science. We think this is really an exciting project. And so in 1992, they commit a significant amount of money to the construction of a piece of big science, a huge observatory to look for gravitational waves. Over the next 10 years, they build the two observatories that are going to make up this project, and they go online in 2002. And so between 2002 and 2010, and during this time there are a couple of upgrades, they try a couple of different things, but they do data runs during this period of time, through about an 8-year period of time. They gather an enormous amount of data, and it's a really interesting thing that they do. They piggyback on an idea out of the SETI community in order to sort of deal with the mountains and mountains and mountains of data they have to sort of go through to see if they get a gravitational wave signal. Now, what the SETI group had done is, it's a project some of you may know of. It's called SETI at Home, and what it is you take these packets of observations, this data from radio telescope observations, and turns out that the processing to look for a signal in these is not actually that difficult to do. It's just very, very, time intensive. And so what they do is they tell everybody, hey, you can download this little program on your home computer. When your home computer's not doing anything else, this program will start up and it'll process data for us, and then it'll send us back the results over the internet. It's called a distributed computing network. And so the LIGO team produces a similar kind of product called Einstein at Home. Instead of SETI at Home, it's Einstein at Home, where you can, by the way, you can go out and download this now and help them process data if you'd like. Just search on Einstein at Home and you'll be able to go download the client. But what happens is that now they've got not just their own computers, they've got millions of PCs around the world processing data for them. And it's a really neat way of doing that. So from 2002 to 2010, they don't get any results. And we'll talk a little bit about why that is here in just a few moments after I go through some of the things that get set up. But they go offline in 2010, and they upgrade the facility to what's called Advanced LIGO. And so in 2015, Advanced LIGO went online, and that upgrade increased the sensitivity of the instrument, of the telescope, about 4 times, going from the old, what they sometimes called enhanced LIGO runs in the late 2000s, to this new thing in test mode. And we're going to talk a little bit about that as well. But the sensitivity increased about 4 times, and it's out of those initial runs in 2015 that this signal that was observed has come. So let's talk about how the LIGO works. So LIGO is what we call an interferometer, or a laser interferometer. Now, interferometry is something that's been around since the late 1800s or so. And it's really the basis of a very famous experiment, sometimes called the Michelson-Morley experiment, where those two scientists were looking for what was known as the luminescence ether, and there's a way of trying to explain why Maxwell's equations weren't working. It turns out they couldn't find it. But the way an interferometer works is, what you do is you take a beam of light and you shine it into a beam splitter, okay? And it's just a piece of optical equipment that takes one beam of light and splits it into two beams of light, each with about half the energy. And then what you do is you shoot those down to a mirror, and the beam bounces off the mirror, comes back, and gets recombined. And when that beam gets recombined, you can look at what's called an interference pattern. So we got to talk about a lot of that and unpack it. So the way the interferometer works is, it's, as we've talked about in our History of the Atom episode, while we certainly know that there's wave-particle duality, light can be thought of as a wave. And so a wave has a characteristic frequency and a characteristic wavelength. And one of the things that waves can do is they can interfere, as we call it. They can interfere with other waves. And so if one wave interferes with another wave, if you think of sort of water waves, we have crests and troughs above the typical undisturbed medium. What can happen is if one wave's crest meets another wave's crest, they'll combine to form a really high crest. The same thing could happen with the troughs. That was what we call constructive interference, and you get big crests, which means you get big waves. If you have destructive interference, on the other hand, what happens is that's when you get a wave crest that meets another wave's trough, and the crest falls into the trough, and they cancel each other out, and there's no disturbance of the medium. And so what will happen is when you have two wave sources creating waves, and there's a point in space where those two waves interact, you can get interference. And if you look at all the points in space where those two waves coexist, you get what's called an interference pattern. Okay, fair enough. Now, the great thing about lasers is they produce this really coherent beam of light. Normal light isn't coherent enough to where you can really do this with this, but a laser produces light that's absolutely, completely coherent. In other words, the waves, all of the photons are in lockstep with each other when they come out of the laser. They all have, the waves are all synchronized so that they all go up and down in exactly the same way, exactly the same time. And so you send this laser out and you hit this beam splitter, and now what you're going to do is you're going to split the beam of light two directions at right angles to each other, and you're going to shoot those down to these mirrors, and they're going to come back, and then you're going to combine them. Now, the mirrors are set up so that they are, in a sense, exactly the same distance from the beam splitter. And so both beams of light will travel the exact same distance, and they'll come back together. And what should happen is, if those two mirrors are exactly the same distance apart, you should get basically an interference pattern that has these two waves constructively interfering to create a wave pattern that's easy and characteristic to sort of look at. Now, if the two mirrors, however, are not exactly the same distance, you're going to get a different type of interference pattern. Okay, and that's how the interferometer works. And I'm not going to go into all the details of what those patterns should look like. They're kind of, tangential to our discussion. So what LIGO does is that, LIGO does this, except what it does is the beam lengths aren't just, in the early Michelson-Morley interferometers, which didn't use lasers but still had fairly coherent light sources. Those were a few centimeters, a few inches in length. These are much, much longer. The two sort of beams, that's 4 kilometers to the mirror, so the beam's going to travel 4 kilometers out, 4 kilometers back on both these legs, as they call them, that are at right angles to each other before the signal's recombined. And so, that's about a 5-mile round trip for each of these things. Well, the idea is that if there are gravitational waves, what's going to happen is that gravitational waves are going to either stretch or compress the literal space-time out of which all reality is made. Okay? And so having these two legs at right angles to each other, what's going to happen is it turns out it stretches one leg and compresses another leg if the gravitational waves exist. And when that happens, what that'll do is that will create a characteristic interference pattern that would be different than the interference pattern that would exist if there was no stretching or compressing. So that's kind of the idea. Now, this is where we really want to sort of talk a little bit about experimental science, because the devil in this is always in the details. So the way this works is experimental science is, you can sit down and, this is what, the guys did when they proposed this. They said, here's how the theory of this should work. This is how we're going to measure it. And in the perfect world where there's no messiness, it should work beautifully. Course, we never work in that world in experimental science. It's always messy, it's always difficult, it's always complicated. And so you set up your experiment and then you spend an enormous amount of time working out all of the details, okay? And I've not done a lot of experimental science myself, but I can tell you, working with students on having them do some simple experiments and having done a little bit of work myself, it is all of those little details that make up all of the difference. It is, especially on a project this sensitive, the details are where everything happens. Back a few years ago, when they thought they had detected faster than light neutrinos, it turned out that result was incorrect. It was an anomalous result created by the fact that a cable way in the back of a processing rig had gotten slightly looser than it should. I mean, it didn't become disconnected. It wouldn't have been easy to see. It just sort of unseated a little bit, this cable, from its socket that it was supposed to plug into, and that created the slightest delay in the electronic signal, and they thought instead that neutrinos were going faster than the speed of light. That's the kind of level of detail in an experimental science you've got to attend to on these super, super, super precise experiments. And this experiment is really, really precise. So what happens is, when you do this, you set this thing up, and you set it up as sort of a proof of concept, and then you start working out all of the bugs that inevitably crop up, okay? That, this equipment rack can't be that close to that equipment rack, or you get signal crosstalk between the two equipment racks. or that you've got to route these cables like this, or you've got to find that out, or whatever the case may be. I mean, in this particular case, since they're dealing with waves, one of the things they have to deal with is dealing with just environmental vibration causing problems, right? And so, when they were taking science data, they actually had to close off the roads around the observatory, because if they had a truck drive on one of those roads, it would create enough vibration in the ground that it would swamp any possibility of them getting to be able to see any sort of signal that might arrive at the observatories. And so you spend a lot of time working on that. And it turns out one of the biggest sort of limitations in this project has to do with just the speed of your electronics. The faster your electronics are, the smaller a signal you can see. And so when they built this thing in the late 90s, they were limited by the electronic speeds in the late 90s. They were also limited by some of the things having to do with how well they could isolate the mirrors from the surrounding environment, some things like that. Well, what you do is you start out and you run at pretty low sensitivity so that you can make sure you got all the kinks worked out in just terms of your experimental procedure. Just as in terms of how you've wired up everything, how you've hooked up everything and all of that. And then you increase your sensitivity over time. And so by the end of, 2010, they had done that. And unfortunately, at the end of 2010, they had not actually gotten a positive signal. Now, that wasn't completely surprising, okay? They thought they might have an outside chance of detecting something if a couple of specific events had happened. But they weren't able to get that, and that wasn't completely unexpected. They sort of understood that their electronics and all of the other things really were not quite up to what they would need it to be. But this project, this sort of original setup, would allow them to get all the things sort of worked out. So when they took everything offline in 2010, that's when they said, okay, we have increased our electronic speeds by over a decade. We've developed other technologies for things like isolating the mirrors from environmental vibration, those kinds of things. And so they went out and they reconfigured the entire thing with new electronics and new stabilization techniques and a whole bunch of other things. And by 2015, 4 years later, they're ready to go again at a better sensitivity. Now, like I say, in the initial runs, what you want to do is you're going to spend time just calibrating the instrument, okay? And again, they're working with new electronics and new stuff, so they got to kind of rework all of their experimental procedures, and that's what they started doing in 2015, was doing what they called sort of calibration runs. These calibration runs meant that the detectors, the observatories themselves, were about 4 times more sensitive than they had been in 2010 when they had taken them offline. But understand that they're actually just as calibration runs. They're not nearly as sensitive as these things are going to be. And so that's kind of what they were doing when the signal gets discovered. And so what's the signal that they see? Okay, let's just quickly talk about that before we get into some other issues. The signal that they see are a couple of massive black holes. I think one of them is 30 solar masses, 30 times the mass of the sun. The other's 50 solar masses, and that these two black holes are in close physical proximity, and they're orbiting a common center. They're orbiting around a single point. And as they sort of radiate out energy as gravitational waves, they spiral in towards each other. And so as they spiral in and get closer and closer, eventually what they do is they merge, and that's very much that merger process produces some energy, and the energy that's produced is a little like dropping that rock in the pond. Now, of course, this is 1.3 billion light years away, so those waves are going to travel for 1.3 billion years. And the interesting thing is, while the waves may have been pretty big close to the event itself, as you get further and further away, they get smaller and smaller. But the neat thing is the two observatories both observed the wave signal come through. And because the two observatories are about 3,000 miles apart, that turns into about a 10 millisecond difference in the arrival times of those waves. So what you're able to do is use the fact that you've got that delay for both of these two telescopes to find the direction of the source. And of course, they were able to do that. And so this is the discovery, and it's a direct observation of gravitational waves. It's you can't say that it's indirect anymore. We have direct observation. It's sort of the direct observation of the final major prediction of the general theory of relativity. And so that's really what got announced on Thursday, is they said, hey, we did this thing, we put this thing together. Our first idea for this was, 30 years ago, 20 years ago, the National Science Foundation gave us the money, and here we are. We found these things finally. And so I want to talk just about, as we get towards the end of our time here, I want to talk a little bit about what this means. First off, there was really a controversy that kind of got involved with this starting in around late 2015, early 2016, first part of this year. A physicist and science communicator by the name of Lawrence Krauss tweeted out that he had heard rumors that there had been a signal, and then a couple of days later he tweeted out, been talking with my sources, and the rumors really do seem to be true. And this ignited this real firestorm of controversy in the physics community and in the scientific community in general. And so let's talk just for a minute about how science communication gets done. The way this is supposed to happen is let's say I'm a scientific researcher, whether I'm a theorist or an experimentalist, but let's talk about this as an experimentalist. And let's say I do a whole bunch of research and I get my data and I do my data processing and all of that. And I come up with a conclusion. Generally what I'm going to do is I'm going to go through a series of steps in terms of getting my results out to the broader scientific community. The first thing I'm going to do is I'm probably going to run those results by an internal kind of review thing. Usually what you do is you give some talks at your local institution, and other scientists will listen to what you have to say, and they may poke holes in what you've done. They may find problems with what you've done, whatever. And if that's the case, you go back and you do better work and you try to resolve those issues and you address their concerns, and then you come back and you do that again. And at some point you kind of get a sense that your colleagues in your institution say, yeah, this looks like good work. And then what you do is you start taking it to conferences. And there might be little workshops, little conferences. You do the same thing, you get the same kind of feedback. And then at some point what you do is you realize you've got good enough work that you're ready to submit this to a scientific publication, a journal, as it were. And what you'll do is you'll publish this in a journal, and the idea of the journal, as we talked about in earlier episodes of the podcast, is you send that to an editor. The editor sends it out to between 3 and 5 anonymous reviewers. The reviewers kind of give you feedback. You don't know who they are. They're not supposed to know who you are, maybe. Though usually the way it works is the physics community is small enough that the reviewers kind of know who you are when the paper comes. So some journals actually leave your name on the paper. But what happens is they give you feedback, you maybe make those modifications, and eventually, if everything goes well, you publish the work. And that's a process that might take as much as a year to 18 months, depending on the type of work and how much review you go through. Well, in an announcement like this, you really can't do that. And so my guess is, and I don't know the details of this specifically, but my guess is they did some internal review at the LIGO sites. And they made sure, and they actually built in some external review committees, and they had some tests that were put in and all of that were really fantastic in making sure that they didn't get ahead of themselves, because they understood they wouldn't be able to go through that normal process. You show up at some scientific meeting and say, oh, by the way, we think we've discovered this thing called gravitational waves. It's the last big thing Einstein predicted, and it's a huge confirmation of his general theory of relativity. That's not something you just sort of drop in before you publish. So the thing that's really interesting is what we know they did is they went out, they did all the internal review they can do, and then they submitted this. And my guess is, when they submitted this to the journal sent this out to probably the largest number of reviewers they felt like they safely could, because this is such a big thing. You want to make sure you cover your bases and do your due diligence. And my guess is, of course, what happened is some of the reviewers may or may not have sort of begun having what I call lunchroom conversations. Oh, by the way, interesting thing I heard, or, I have some inside information. Now, back in the days before we had things like social media, that kind of conversation happened all the time. You might sit in the lunchroom or, over dinner, or just, after a seminar and say, well, here, I've kind of been looking over this paper, and I think that probably, and you might not say a whole lot, and you wouldn't allow anyone to scoop you, though that sometimes did happen. But my guess is that got out, and Krauss heard about it. Now, Krauss then tweets out his rumors, and he gets a huge amount of backlash. And the backlash really came in sort of 3 ways. So the first one was, is talking about science rumor okay? Okay, and there were a lot of people that took him to task that said, hey, look, none of this is necessarily peer-reviewed. You have no business to talk about this, because if it turns out it's wrong, or your rumors are not true, well, then it looks like it's just another failure for science in a highly skeptical and science-scared world, and you've done the practice of inquiry a lot of harm and damage. And Krauss's response was, hey, look, I clearly said in my tweet that these were rumors and nothing more. And so, that's not a big deal. And so there's a lot of conversation about that. And one of the things is probably, I think there's probably some truth in the idea, the criticism of the argument against this of, he did some, if this had been wrong, he would have done some massive harm. I'm not sure that's true. Okay. He's not a nationally recognized figure that shows up on, the NBC Nightly News or something like that. He wasn't a Neil deGrasse Tyson type of figure. And secondly, this is such a tiny drop in that particular controversial bucket. People are going to accept the results of science or not accept the results of science based on much bigger factors than whether this guy tweeted out something about gravitational waves. The second question that came up, and this one may be a little more germane, is Twitter a valid form of scientific communication? There are a lot of people that took Krauss to task and said, look, you don't communicate scientific results via Twitter. That's just not how it's done. And then Krauss said, well, hey, look at what NASA's doing. Look at what ESA is doing on all of their space missions and all of their space probes. They're tweeting out this sort of non-scientifically specific information about what various rovers and landers and space probes and all of those kinds of things are doing. How is this any different? And his argument, and I think there's some truth to this, is we live in a different age of communication. And so we need to sort of adjust some things that we're doing in the world of scientific communication to reflect that, especially when scientific agencies are already tweeting out information about, the work going on in their things. Nobody's going to confuse a tweet with a scientific publication. And so because of that, his tweet didn't really violate anything. The third argument, and this one I think probably maybe of the three has the greatest sort of human impact in the scientific community, he sort of stole the LIGO people's thunder. As he put that out, all of a sudden a whole bunch of people got really interested in it. Really, and he didn't ever took credit for it, but it was one of those things where it's kind of like he scoops those guys a little bit. And, when they do get up to give their announcement, everybody kind of already knows what's coming. Well, and that's maybe a little unfortunate. And that's, if I'm going to criticize Krauss as a scientist, that's the biggest thing I'm going to criticize him for in his tweet is, look, let me take credit before you start putting stuff out there. Now, Krauss's response and some folks in scientific communications response is, look, actually it did the exact opposite. By putting that out there, it generated a lot more buzz. And in generating a lot more buzz, there were a lot more media outlets that keyed in on this story and were at the press conference where the results got announced. So in a way, this is like releasing a trailer for a movie. It generates buzz for the movie before the movie actually comes out and increases the possibility that people are going to pay attention. And he might have some legitimate sort of points there. Anyway, it's a controversy I think this is not going to go away. This is not something, by the way, that got resolved in any of the sort of back and forth between the various parties about this, but it was really an interesting thing. And I think in science, it's an issue that we are really going to have to come to terms with to some degree. The idea that the scientific publication system is something that was, developed in the 1800s, evolved and changed through the 1900s. Peer review became a big part of the process after World War II. But all of that creates a fairly slow communication process for good reasons in many cases. But maybe there's time for us to begin to really rethink some of those ideas. And there is a conversation that's taking place in that. In terms of the guys at LIGO, they did everything that was absolutely right. They took their paper, they did internal review, they did all the stuff they're supposed to do. They then submitted it to the journal. The journal took it through the correct process. They did not announce their results until the paper was published by the journal. And that's exactly the way you should do scientific results. That's exactly how they did it. It is really, really phenomenal of them not to have jumped the gun in any way, shape, or form. That's not always the case in science. Sometimes people get pretty excited and they jump the gun on this thing. The guys at LIGO did it right, and all kudos to them for that. So let's talk about here as we close out. This podcast is getting close to an hour now, and I'd like to wrap it up before we get to an hour. And that is, how important is this work? Why is this a big deal? Now, the thing that sort of captured the national news is, hey, they discovered gravitational waves. For us in the scientific community, that's only sort of big news. We kind of knew they already existed from the indirect observations, made back in 74 by Hulse and Taylor. That's not something for us that was a big deal. The bigger deal is that this is a new kind of observatory, and we've now shown that we have a new kind of observatory. This is a new kind of telescope. And so it opens up a new window to the universe for us that we did not have before. And so I want to take just a brief digression here to talk about what happens when you have new ways to observe. And in one of the early scientific method episodes, I sort of likened the process of hypothesis, law, and theory formation to putting a puzzle together. That you've got this puzzle and you're trying to put it together, and it's got an awful lot of pieces and it's pretty big. And the thing that's really interesting is, let's say this is one of those 10,000 piece puzzles that they you occasionally can buy on the internet. Well, the thing that's interesting is when you get that a puzzle, you assume you have all 10,000 pieces. You just got to fit them in the right place so that the picture emerges, right? Well, what if when you bought that puzzle, what the person selling the puzzle says, well, okay, you can get the pieces of the puzzle, and we're going to send you the first 5,000. But in 5,000 more, we're not going to send you unless you can solve certain mind riddles or, certain games, or you go to visit certain sites or whatever. And then, at those, when you do those things, we'll send you another 100 pieces or another 1,000 pieces or whatever. That's actually a little more like what happens in science. So what happens is you work with the puzzle pieces you have, but there are going to be holes in the picture. Now, in some cases, what you can do is you can say, okay, there are holes in the picture, but I can infer what's inside those holes by what I see from the pieces around those holes. And sometimes what you may say is, they're just whole chunks of the puzzle. I don't even know what's going on. I mean, they maybe are there. You may not even know they're there. And so every time we've created a new technology, it allows us to get more of these puzzle pieces. It's like solving that puzzle. We create a new technology. The manufacturer sends us another 1,000 pieces. We can put them into the puzzle. So, the big idea that I always talk about in terms of astronomy is when you do astronomy, when you first did astronomy, all we had was our naked eye. And so when all you have here is your naked eye, the picture you put together is based off the data you gather with your naked eye and nothing else. And we got surprisingly far with that, but, that kind of gets hung up in the period before the 17th century, okay? Well, it's just not much farther we can go with our naked eye, even with the great instruments that had been produced by that point by guys like Tycho Brahe and some others. When the telescope not only gets invented, but then gets used to do observational work by Galileo Galilei and a number of other parties, well, all of a sudden that opens up a whole new part of the universe, and now all our models start to change. Now, the thing that's interesting, though, is, of course, we're still using just our eyeball. So, later on, after, we sort of continue to do this, when in the 19th century we begin to develop photographic techniques, we can take light and we can store it on a plate. Okay, well, that allows us to do some things that we can't do, and then all of a sudden we're able to do more with the universe. And then we begin to realize that we can take light and we can break it into a spectrum, and that allows us to do some things. And every time you get a new advance, well, you get more data. Well, the big one that happened in optical astronomy is when we started developing cameras and technologies that allowed us to see in other parts of the spectrum that our eye couldn't see. And all of a sudden, the universe really began to change. Our understanding of it began to change, especially when we were able to look in both the ultraviolet and infrared parts of the spectrum. This observatory has the potential to do a similar kind of thing. Okay, there are all kinds of processes out there that we may not be able to observe, either because we can't observe those wavelengths of light, or more importantly, maybe they don't interact in wavelengths of light at all. The great example of this would be, we know there's this stuff called dark matter, and we can sort of get a sense of what that dark matter looks like in some respects by how it bends visible light. But the reason the matter is dark is it doesn't create light that we can see. Well, if it's mass will produce gravitational waves, and it may turn out that if we've got large conglomerations of this dark matter, and they produce gravitational waves that are strong enough, we'll be able to see that dark matter using these gravitational wave observatories in a way that we could never have done with an optical telescope. Okay, and that's the type of thing that we're talking about, and that's the thing that for most of us in the astronomical community, that is what's really, really huge. I had someone ask me, how important did I think this particular observation was? Where does it rank in terms of some of the big observations? And that's going to be hard to tell right now. I mean, we've just gotten the observation. We don't know all of the details of where this is going to take us. So right now what I say is it sort of ranks up there with two observations in the last 20 or 30 years. One of those is neutrino oscillation, where we now know that neutrinos can change from electron neutrinos to tau neutrinos, or whatever the case may be, that there is a way those guys oscillate back and forth, and that tells us that those neutrinos probably have mass, though it's still too small for us to be able to measure how big that is. That was a big discovery to see that. The other big discovery in the realm of physics was, of course, the discovery of the Higgs boson. And I think this may rank right up there with the discovery of the Higgs boson. And the reason is that neither of those things changed our understanding of the universe, but they confirmed some of the really out there theoretical pieces that we've been working with. Neutrino oscillation and the discovery of the Higgs boson confirming certain aspects of the standard model of the universe, or certain versions of the standard model of the universe, or standard model of particle physics, maybe is a better way to say that. This, of course, is the last great confirmation of the general theory of relativity. But there's this other piece, and that is that this is a new technology to observe the universe. And so it may turn out we don't actually observe a whole lot at all, and this just becomes another type of telescope, like a neutrino observatory, or maybe like a radio telescope as compared to an optical telescope, something like that. But if it turns out there are whole pieces of the universe that we haven't ever seen, and this opens that up for us, then I'm going to elevate this to a much greater discovery. This may be something in 50 years we look back on and we say this was a massively watershed, result that came out. And then, then it might get elevated to something like, our discovery of wave-particle duality or something like that. So how important is this? I think this is probably one of the three major accomplishments now of the last 30 years, but not more than that. It's not something that's, epical in a sense that it really changes thing, but that remains to be seen. And we're going to see what the results that come out of this experiment are, and how that changes stuff. And if we get more and greater results, then that may be a bigger deal. And remember, these results came out of calibration runs. They didn't come out of the instrument operating at the full level of its new sensitivity. From the information that I've been able to gather, we're not gonna probably get the full sensitivity, I think, until 2021. So we're definitely gonna be able to, this observatory will become much, much more powerful, and we may see some things out of it that are really quite remarkable. So certainly something to sort of kind of keep an ear to the ground on, and follow us here at the Scientific Odyssey. If the telescopes make great discoveries, we'll certainly pass those along to you. So as we approach the 1 hour mark here, we're going to go ahead and wrap this up. Next week, you can sort of expect us to drop back into the standard narrative. Like I say, we're going to talk about Babylonian astronomy, and we're going to continue to look at the development of how we know what we know about the sky and what that tells us about our place in the universe. So I hope you'll stay with us, and we'll continue that. If anything else comes out, we'll certainly let you know what's going on with that. Also, I'm sure the big science shows are going to come out with episodes on this, so certainly go out and listen to those if this has piqued your interest. So, as always, y'all, thank you very much for listening. I hope you've enjoyed this brief digression into something a little different, and we'll get back to our more normal programming in a week. So until then, full sails on your journey.